So hello everyone, welcome back to my channel Crazy Physics. So I'm right now uh, driving a course of advanced quantum mechanics, and in the previous classes I have informed about that first order and the second order time independent perturbation theories and corresponding problems over there. And now we will proceed to the next segment of this advanced quantum mechanics, that is the degenerated perturbation theory. So till now we were talking about the non-degenerate cases where there is the energy difference between the two energy eigenstates. But when it comes that both the eigenstates are energy eigenstates and the corresponding eigenstates are always the same, then what will happen? Then we know that from the first order and the second order time independent perturbation theory, we know that in the first order case it is like psi n, this is the perturbation energy, divided by En minus Em, right? And for the second order it is same as that, but with modulus square over the numerator part, and the denominator is the same. So in the first order and the second order perturbation theory, we easily see that there is a energy difference between two energy states, which represent the denominator for both the cases. But when it comes for degenerate cases, so it will become zero. So the energy corrections will be infinite according to the theory. But we have to break these things to get the exact and the real result. So let's start from a twofold degeneracy case. Okay. So what is the twofold degeneracy case? We have two eigenfunctions, psi 0 and psi 0a and psi 0b, and if we operate a Hamiltonian with unperturbed state, we will get a energy eigenvalue Similarly, if we operate A0 on psi B0, we will get the same amount of energy for this different eigenstates. Okay, so we are getting two same energy as eigenvalue for different eigenstates. So these are the degenerated energy states, and these are called a twofold energy. So what happens is that if we plot a graph here, this is E0, this is the energy, and this is, we suppose that this is lambda, which is the parameter we have used for perturbation. This is called, you can say, a parameter that responsible for the perturbation. We can turn it to 0 or to 1 for getting the perturbed state. Okay, so this will be like this. So for lambda value 1, for highest point, it will be like this. So there is a twofold degeneracy over there. By tuning this lambda, we can get the what is perturbed or unperturbed state. Okay, so H prime is the perturbation which will break or lift the perturbation by tuning the lambda from 0 to 1. If we go to 0, then there will be no perturbation. If lambda is greater than 0, then there is a perturbation. So that's why E0 can be split into two degeneracy points, and when lambda tends to 0, there is no perturbation over there. Then what will happen, that upper state will come down towards then, and there will be only a single line over there, and there this point also converts to this point, this line. Okay, so this will come there, this will come there, and it will be a linear combination of eigenstates. It will be a eigenstates of linear combination. So next we have to find the good linear combination. What is called as the good linear combination? Let's see. So for the good linear combination, the definition of good linear combination is that the states which are defined as the limit of the true eigenstates as the perturbation is switched off. Okay, so we can get the true values of the eigenstates when there is not a single perturbation there. So that is the good quantum state, good linear combination of eigenstates, and I will discuss about that in my next video. So let's try a example to get a good linear combination. Okay, for a two-dimensional harmonic oscillator. So this is the problem here. This is H. This is the without perturbation Hamiltonian of the two-dimensional harmonic oscillator. P square by twice m of mass m plus half m omega square x square plus y square, where omega is the characteristic frequency of the oscillator and x square plus y square because it is two-dimensional harmonic oscillator. So now if we apply a perturbation H prime such as epsilon m omega square xy, and in this case the first excited state without perturbation is 2h cut omega. Okay, and we are given two wave functions psi a and psi b0. So we have to find the linear combination between psi a 0 and psi b0. Okay, for this 2D harmonic oscillator. So we can write the Hamiltonian as this. H quad square by twice m del x plus del 2 del x2 del 2 del y2 plus half m omega square x square plus y square. Okay, so we are writing this equation as this, and now we will use rotating coordinates. So rotating coordinates is used to simplify the time dependent or independent problems by transforming a complex or rapidly oscillating system into a simpler frozen or slowly varying frame. Okay, so the main goal of introducing the rotating frame of reference or rotating coordinates in this system is to freeze this system, this rapidly varying oscillating system. Okay, so next we will introduce the rotating coordinates and we'll find the required result for this. So if we introduce the rotating coordinate system x prime as x plus y by root 2 and y prime as x minus y by root 2. Mainly we are rotating the frames x and y for 45 degree. These are the things of cos 45 degree and the sin 45 degree whose values are 1 by root 2, so y divided by 1 by root 2. And after applying the perturbation and the rotating coordinates, we will finally get the perturbed Hamiltonian as this h cut square by twice m del 2 del x prime 2 plus del 2 del y prime 2 plus half m 1 plus epsilon omega square x prime square plus half m 1 minus epsilon omega square y prime square. So this amounts to two independent 1D oscillators. Two independent, we can use this as this one and this one as a independent oscillator, this one and this one as another independent oscillator. So using two independent 1D oscillator approximation, we will get a wave function like this. A wave function of function x prime, another wave function of y prime. Okay. So for psi mn plus minus, there will be the characteristic frequency like this. Okay. And corresponding energy eigenvalue will be m plus half h cut omega plus n plus half h cut omega minus. Okay. So let's see three different cases over here. For E00, we code as 1. E01, we will code as 2. And E10, we will code as 3. This is the states where there is no perturbation. And there are the states, there are some perturbation exists. So what will be the plot over here? The plot will be like this. This is 1, this is 2, this is 3. There is no perturbation. This is simply a straight line over here. When there is a perturbation for 0, 1, so it will be doubly degenerate, and for the case 3 it will split into 3 degenerate states over here. So here 0 zeros, I mean m equal to 0, n equal to 0, m equal to 0, n equal to 1, m equal to 1, n equal to 0. So these are the plots of corresponding these energies. If we have m equal to 0, n equal to 0, that will be 0, half h cut omega plus, half h cut omega minus. So there is a linear plot there. For m equal to 0, n equal to 1, there is two types of degeneracy, and where there is m equal to 1 and n equal to 0, then for omega plus over here, that for characteristic frequency the positive side, there will be 3 distinct degenerate states. So now we have to find the linear combination to get the required answer of this problem. So for limit epsilon tends to 0, psi 0, 1 will be limit epsilon tends to 0, psi 0 plus x prime into psi 0 minus, sorry, psi 1. This is 0, 1 first case, okay? So for this y prime, if we come back to the initial coordinate system, so we have to rotate another time. So we will get this as the required eigenstates, and this will give us a result m omega by 2h cut x square plus y square, which is minus psi a 0 plus psi b 0 by 2. Similarly, for psi 1 0, for limit x epsilon tends to 0, for that it will be this will be 1, this will be 0, so the vice versa case will happen, and we will get root over 2 by pi m omega by h cut x plus y by root 2 into e to the power minus m omega by 2h cut x square plus y square, which will give us psi a 0 plus psi b 0 over 2. Okay, so finally the required example will be, sorry, this is over 2, this is normalized condition, right? So the required result will be, 1 by root 2 psi b 0 plus minus psi a 0, which is the required linear combination for the two-dimensional harmonic oscillator. So this is for this video. Now we will proceed the next to the next video about the next things of this this two degenerated perturbation theory. Still then, please stay tuned on my channel, and please subscribe and share to the your colleagues, and thank you so much for watching.